Up to now, we have introduced the Fourier series, but we have not discussed the convergence of a Fourier series. Now it's time for us to study this problem. Uh, so uh, the basic result for studying the convergence of Fourier series is the Riemann Lebesgue lemma. Riemann Lebesgue lemma. Assume that f defined on the interval has at most a singularity b. That is, for any say in AB, f is integrable in maybe on AC. Okay, so this is what we say it has at most a singularity. Of course, if you have more than one singularity, you can, for example, A, B. If you have several singularity, you can finitely many one. You can consider divided the interval AB into several sub-interval and apply the result that we will prove in this lemma. Okay, so that is if f has more than one singularity, the result is also true. Okay, so another requirement is that the integral f is absolutely integrable over AB. Then we have as p goes to 0. P goes to infinity. So this result is called the Riemann Lebesgue lemma. As a corollary of this lemma, we know that f for f in L, we know that we can construct the Fourier coefficient ak, that is pi over minus pi fx cosine kx dx. Now, as a special case of applying the Riemann Lebesgue lemma, we know that this goes to 0 as k goes to infinity. We get this result for f at 2 and applying the Bessel inequality, right? But if f is not L2, you could not apply the Bessel inequality. So whether the Fourier series converges to 0 is unknown. But having establishing this Riemann Lebesgue lemma, this is confirmed to be true. Okay, so from this remark, we know that the Riemann Lebesgue lemma is very useful. Okay. Now, if you also play a central role in our argument about the convergence of Fourier series, now we prove this lemma. Prove because the integral is converged for any epsilon positive. We can choose say in AB such that the absolute value of fx cosine px dx. Of course, this will not greater than fx, and this is very small. The convergence of this integral means that the limit exists. C goes to b. From the left, say b. Oh, sorry, no. AC. This is exactly the integral at AB. Therefore, when C is very close to B, the integral in this part is very, very small. It can less than the prescribed small positive number epsilon. So first we taken C. Having taken this C, having estimate the integral over the interval CB, we can focus on AC. The advantage of considering the problem in AC is that in AC, our function is integrable in the Riemann sense, in the usual sense. Therefore, this will be easy to tackle. Okay. Now, since f is integrable over AC, we use the RAC to denote the integrable functions over the interval AC. Okay. Then, by the result of from the series of integrals, we know that there is a partition. When studying integral, we need to use partition. P, that is xi, I from 0 to n of the interval AC, such that omega I delta xi is small. Okay, where omega I is the oscillation of f in the subinterval. So this is A, this is B. We have a partition. This is xi minus 1, this is xi. So this is a typical subinterval. Omega I is the oscillation of f on this interval. That is, omega I is supplement of xi minus 1 xi f subtract infiniment. So since f is Riemann integral in AC, therefore we can take a partition of AC so that the sum of the oscillation area is small than a given positive number epsilon. Okay, then we have the following result. Xi minus 1 xi cosine px dx. This integral can be computed explicitly. That is sine pxi minus sine pxi minus 1 over p. Then this will not greater than 2 over p. Okay, this will not greater than 2 over p. Now we can estimate. We want to prove that the integral of f cosine p in AB is very, very small. We already know that it is very, very small from A to B. Therefore, we need to prove that the integral from A to C is also small. Okay, this is what we want to do. Now, we estimate this integral for this purpose. AC fx cosine px dx. To estimate this integral, we write it into subinterval xi minus 1 xi, and fx minus fxi cosine px dx. We insert a number here, and then of course we need to subtract this. So we have plus the integral xi minus 1 xi fxi cosine px dx. Okay. And this will not greater than the absolute value of the first part and the absolute value of the second part. So in this interval, in this integral, the fxi does not depend on x, so it can be moved outside the integral. Okay, therefore our this estimate is the sum of fx minus fxi. Okay, the first integral here, you can take the absolute value inside the integrand. The integrand cosine px is absolute value is not greater than 1. So the integrand is controlled by fx minus by the absolute value of fx minus fxi. So dx. Plus the second term. The second term we already move fxi outside. So taking absolute value, this will be I from 1 to n fxi. Then absolute value of xi minus 1 xi cosine px dx. Okay, so we have this inequality. Now this will not greater than this part. This part x is in xi minus 1 xi. Therefore, the absolute value of this will not greater than the oscillation of f on the i's subinterval, that is omega I. Okay, so I have to go to next page. So the first term will not greater than this integral. Let's have say more. This integral, the integram is not greater than omega I. Therefore, the integral will not greater than omega I multiplying the length of this interval. That is delta xi. Delta xi is xi minus xi minus 1. Okay, so this will not greater than omega I multiplying delta xi. So we have omega I delta xi for the first term, for this term. Okay, because the integram is controlled by omega I. So the integral will not greater than omega I multiplying the length of the interval, that is delta xi. Therefore, the first term is controlled by this oscillation area. For the second term is this. For this, the absolute value of the integral of cosine px will not greater than 2 over p, as we estimated before. Okay, so the second term will not greater than 2 over p sum of fxi. And by our choosing of the partition P, our partition P makes the oscillation area the sum of omega I delta xi small, less than the epsilon. So this less than epsilon plus 2 over P. But the partition P, capital P, sorry, we have a small p, cosine small px, but our partition is denoted by capital P. Not confused. Okay, so our partition P is given. Given epsilon positive, we determine this partition P. So the point xi, I from 0 to n, are fixed. So this is a given number. This is a fixed number. But P can be changed. The small p can be changed. So this will not greater than 2 epsilon if P greater than some P0. Okay, so once small p is large enough, we see that once small p is large enough, then the absolute value of the integral from a to c is less than 2 epsilon. Linking all our estimate, we get this conclusion. That is given epsilon positive, there is a P0 positive. If P is greater than P0, then a to c fx cosine px dx is less than 2 epsilon. Therefore, our a to b fx cosine px dx, of course, will not greater than a to c plus c to b. C to b is less than epsilon by our choice of c. We take a c so that given epsilon positive, we take the c so that the integral, the absolute value of the integral over c to b is less than epsilon. Okay, so fixing this c, we also take a partition P so that the oscillation area is less than epsilon. Therefore, the integral from a to c is less than 2 epsilon once the P is large enough. P large enough so that the second term here is small, so that altogether can be controlled by 2 epsilon. So this will get smaller than 2 epsilon. Therefore, in conclusion, this is smaller than 3 epsilon. So we have proven that given epsilon positive, we can find a P0 positive. So that once small p is greater than P0, then the absolute value of our integral will not greater than 3 epsilon. So this proves that the integral goes to 0. And our p might be negative also. So we should add absolute value here. We should add absolute value for this p, and also finally for this p. So this is also its absolute value, maybe absolute value, sorry. So this proves that once the absolute value of p is large enough, our integral is less than previously given small number. So this proved the conclusion of the Riemann Lebesgue lemma. Okay.